Our session today talks about the selection of strength parameters for stability analysis of mining earth structures. So one of the factors that has resulted in slope stability failures of mining earth structures has been the mischaracterization of the available shear strength. Dr. Morgenstern, in his 2018 the Mello lecture, reflect on the cause of tailing facility failure and note that, quote, inadequate understanding of undrained failure mechanism lead to static liquefaction with extreme consequences consequences is a factor in about 50% of the cases. End of the quote. This lecture explains the reasons for the difference between the effective stress and undrained strength parameters for soil and tailings in consideration for selecting appropriated parameters for stability analysis of tailing dams and other mine structures, such as mine waste dams and heap leach pads. For today's lecture, we have with us Engineer Scott Martens. He is the Director of Tailing Engineering in Teck Resources, providing cooperative oversight of tailing engineering at Teck operating mines, develop projects and legacy facilities across North and South America. Scott has 29 years of geotechnical engineering experience with 15 years in consulting and 40 in geotechnical mining operation. His focus has been on design, construction, safety assessment of tailing, hydroelectric, and irrigation dams. Prior to joining Teck, Scott worked extensively in the Alberta oil sands, leading a team of engineers and geologists responsible of the design and construction of mine tailing facilities, mine waste dams, pit slopes, geology and hydrological at large oil sand mines. Scott has a Bachelor of Civil Engineering degree from the University of British Columbia and a master's degree in geotechnical engineering from the University of Alberta. He is also an adjunct professor here in our center at the Geotechnical Engineering Center at the University of Alberta, and he is a member of independent review board for the tailing facilities at a gold mine and is the chair of the Mine Dams Committee for the Canadian Dam Association. So with this, just join me welcoming Scott.
Okay, thank you, Daniel. Is my audio coming through okay?
Yes, it is.
Okay, great. So thanks for that introduction. So today's talk arose from observations that I and others have had with the state of practice in selecting strength parameters. It's really just a summary of the work by many esteemed geotechnical engineers. I'm not presenting anything new today, but hopefully I can present it in a way that is helpful to better understand the topic. This is about the fundamentals. If you were looking for the latest research on advanced constitutive models, you're in the wrong lecture. The focus of this talk is about understanding undrained shear strength. And why we're talking about this, because as geotechnical engineers, we need to understand the different representations and tests for strength in order to use the correct parameters for stability analysis. I've seen many cases where people use drained or undrained strengths incorrectly because they didn't fundamentally understand what they really meant. And this has been a learning journey for me as well. I don't profess to understand everything about soil strength. And then in the discussion time at the end, I'd invite other attendees to provide their insights as well. So for context, this discussion on undrained strength is relevant to clays, silts, and sands. And to give away the ending, sands can shear undrained if they're contractive. And that's contrary to the belief of some engineers and even some well-known publications. So we're going to examine how this is. As Daniel noted, Dr. Morgenstern in his Mello lecture reflecting on the cause of tailings facility failures noted that inadequate understanding of undrained strength mechanisms was a factor in about 50% of the cases that he looked at. And in my practice, I consistently see cases where the strength of loose sands is incorrectly characterized with effective stress parameters based on the mistaken understanding that the choice of drained or undrained parameters should be based on permeability. Undrained failure mechanisms where the physical causes of the failures in several notable recent instances, including the very tragic Feijão Dam failure at Brumadinho in Brazil. And there was a 2014 study before that failure that calculated the factors of safety in the drained condition to range between 1.6 and 2.1, but the undrained factor of safety was just above 1, and the post-liquefaction factor of safety was much less than 1. Undrained failures can occur very rapidly with little or no indication of distress. And we know that soil behavior is governed by effective stresses, but as we'll discuss, an undrained strength analysis is useful when you don't know the effective stresses at failure, particularly the effective stresses that are mobilized during shearing. So here's an outline of what we're going to cover. My discussion is going to be in the context of mine tailings dams, but the principles are applicable to other types of dams and embankments, waste dumps, tailings dry stacks, heap leach pads, such as the failure that occurred a few weeks ago in Turkey. And all of the external figures that I've used are fully referenced so that you can easily find the source and do further reading. And I'll take questions at the end of the presentation. So I'm going to use stress path diagrams as a basis for understanding drained and undrained shear strengths. And we're going to start with a refresher on Mohr circles and stress paths. Sorry, the laser out here. Okay. So a Mohr circle represents all of the two-dimensional or axisymmetric states of stress in an element of material. It's obtained by plotting the principal stresses on the horizontal axis and shows the shear stress on the vertical axis. Remember that the principal stresses are the stresses on planes that don't have any shear stress. Sigma 1 is the major or largest principal stress, and sigma 3 is the minor or smallest principal stress. And the points of tangency to the Mohr circle define the failure envelope and represent the most critical combination of shear and normal stresses within the specimen. Here you can see a series of Mohr circles defining a failure envelope. These are from the test data from the Fundão Tailings Dam failure investigation. Mohr circles can be plotted for total stresses and effective stress conditions. The effective stress is equal to the total stress minus the pore water pressure. And since the pore water pressure acts equally on both principal stresses, a positive pore water pressure simply shifts the Mohr circle to the left. Negative pore water pressure would shift it to the right. And the tangents to the effective stress Mohr circle define that effective stress failure envelope. Now we'll take the Mohr circle concepts and extend them to stress paths, which are extremely useful to understand soil behavior. A stress path takes the information from a Mohr circle and represents it by a single point, so that it's possible to track the evolution of the stresses during a lab test or the stresses in the ground during a change in loading. The top of the Mohr circle is a convenient point to represent the stress state, and that's the point on the stress path. So a conventional drain triaxial test, where the confining pressure, sigma 3, is held constant, and the vertical pressure, sigma 1, is increased, looks like a set of expanding Mohr circles, or a stress path at a 45-degree line. Another way of representing the failure condition is to link up the top of the Mohr circles. A line through the top of the Mohr circles yields a different slope than the failure envelope that joins the tangent points. That's the blue line, but it's just another way to express the same failure condition. The red line through the top of the Mohr circles has an angle alpha, not phi, but the difference between them is given by this relationship at the top. And don't confuse the two. There are two commonly used coordinate systems for stress paths, the MIT and the Cambridge coordinates. They're based on the same information, but the slopes of the lines are different. The MIT coordinates tracks the top of the Mohr circle. That's what I showed in the previous slide. It uses the variables S primed and T for confining pressure and shear stress. And in triaxial compression, the total stress path rises at a 1-to-1 slope. The Cambridge system also accounts for the intermediate principal stress. It uses the variables P primed and Q for the confining pressure and shear stress. And in triaxial compression, the total stress path rises at a 1 horizontal to 3 vertical slope. The PQ coordinates are used in most advanced soil models, such as Norsand. But I'm going to primarily use the ST space diagram in this talk because it makes the concept slightly easier to understand, though they could equally be expressed in PQ space. Unfortunately, some people and some texts use the MIT definitions, but the Cambridge labels, which can lead to all sorts of confusion. So don't be sloppy with variable definitions. And when you see a diagram labeled PQ, just check to make sure how the authors have actually defined those variables. So the behavior of a soil during shearing depends on the density. A loosely packed contractive soil on the left densifies during shearing. The particles try to move into a denser arrangement. If the voids are filled with water, it is either expelled from the soil, or if drainage is inhibited, the water pressure increases. A dense, dilative soil does the opposite. The soil particles try and ride up and over each other during shearing, increasing the size of the voids and drawing water in, or creating negative pore water pressures. And there's an equilibrium state in which the particle arrangement neither contracts nor dilates during shearing. That's the critical state, and soils will reach that state if they're sheared far enough. Like Moore's circles, stress paths can be plotted for both total and effective stresses. Here you can see the total stress path and the effective stress path for triaxial compression, where the lateral stress is constant and the vertical stress increases. Remember, these are just representations of the total stress and the effective stress, Moore's circles. The horizontal difference between the total stress and the effective stress path is the pore water pressure. For drained loading, the total and effective stress paths are the same. There's no excess pore water pressure. For undrained loading, they will differ based on the pore pressure generation during shearing. If the soil contracts during shearing, as is shown on the left side figure, the pore pressure will increase and the effective stress path will plot to the left of the total stress path. If it dilates, the pore pressure will decrease. And dense soils, such as shown on the figure on the right, often contract initially and then dilate, as shown by the dotted line. And that's the negative pore water pressure to failure. So now we'll talk a bit about drained and undrained strengths. This figure shows drained and undrained triaxial tests on loose and dense soil. You can see that the endpoint of the tests all trends towards the same line, which is the effective stress critical state stress ratio, or friction envelope. For the loose sample, the undrained test reaches that failure envelope at a much lower shear stress than the drained test. This is because it's generating excess pore pressure as it shears, and that's the excess pore pressure there to failure. So that Moore's circle is shifting to the left until it hits that failure envelope. If the soil is dilative and there is negative pore water pressure, you can see over here, then the undrained strength will be greater than the drained strength. That friction envelope isn't a strength. It's a relationship between the shear strength and the state of stress. Although each set of drained and undrained tests are on the same samples, the strengths at failure are very different. And the critical state strength is that strength after relatively large shear strain when there's no longer any volume change with additional shearing and the straining continues indefinitely at the same shear stress. The critical state friction angle is a material property. No matter how you shear the sample or under what stress conditions, you'll always eventually end up on that line. But the shear strength can vary dramatically anywhere along that line, depending on what stress path is followed. So consolidated drained and consolidated undrained triaxial tests will both give the same friction angle, and that's why we can get effective stress parameters from both drained and undrained strength tests if you measure the pore water pressures for the undrained test. This figure shows the results of drained, which is the red line, and undrained, the green line, triaxial tests on loose sand. Again, you can see that the endpoint of the tests all trend towards the same line, which is that effective stress critical state friction envelope. But in this case, the undrained strength is 1/4 of the drained strength. To repeat, that friction envelope isn't a strength, it's just the relationship between the shear strength and the state of stress. So effective stress parameters provide an envelope that allows the strength to be calculated from stress conditions. For a limit equilibrium analysis, you take the normal effective stress on the slice bottom and use the failure criteria that you developed to find the available shear strength on the base of the slice. The water pressure for the effective stress calculation is based on the distance from the water table to the base of the slice, or a specified RU or B bar value to represent the water pressure. But the shear-induced pore water pressure is ignored in that calculation. And if there was shear-induced water pressure, you don't know what the effective normal stress on the slice base is. And hence you don't know where you are along that line. The way to deal with that is to use undrained strength parameters, which include the shear-induced pore water pressure in the strength. If you have assumed drain conditions and there's significant pore water pressure generated during shearing, the undrained strength can be much less than the drained strength. This slide here is from Mike Jeffrey's lecture on critical state soil mechanics. And when he presented that, the slide was titled, "Why Dams with a Factor of Safety of 3 Fail?" Well, they fail when the shear strength parameters that are assumed aren't what are actually available. In this case, the drain strength is about 3 times the peak undrained strength and about 7 times the residual undrained strength. So since we know that soil strength is governed by effective stresses, why not just calculate the shear-induced pore water pressures and use those in the effective stress stability analysis? Pore water pressure response during shearing can be estimated from triaxial tests using Skempton's A and B parameters. The B parameter relates the pore water pressure change to the change in mean confining stress, and it's a function of the degree of saturation. The A parameter relates the change in pore water pressure to the change in shear stress. That's the parameter we need, but it varies along the stress path to failure. There isn't a constant value of A for a soil. You can see this in the bottom plot here, how the shear-induced pore water pressure varies as a function of strain and soil density. So we've got 3 different densities here, loose, medium, and dense. The field drainage conditions and local variations in soil gradation, stiffness, and other properties make it difficult or impossible to accurately predict the pore pressure response during shearing at the scale of a potential failure. So far we've been looking at triaxial compression stress paths, but the end-range shear strength is not a material parameter. There isn't a single undrained shear strength associated with the soil at a particular location. It depends on how the soil is loaded, and to understand and select the appropriate undrained shear strengths for design, you have to understand the stress path. In triaxial compression, the lateral confining stress is constant and the vertical stress increases. You can see the increasing more circles there and the stress path to failure. In lateral extension, the vertical stress is constant and the lateral stress decreases. And that's that stress path. They both reach the same failure envelope, but at much different shear stresses. In a drained analysis, that all gets sorted out in the relationship between normal stress and friction ratio. But in an undrained analysis, you arrive at a specific strength from the test. So the stress path in the lab needs to follow what's going to be happening in the field. Two more stress paths are axial extension, where the horizontal stress is constant and the vertical stress decreases, and similarly lateral compression. For the latter two, sigma 1 and sigma 3 switch, and by convention, these are plotted on the negative deviator stress axis. These are all total stress paths that I've shown here. As we've seen, if the soil is contractive, the mobilized strengths will be lower than what are shown here because the effective stress path is going to shift to the left. What I've shown so far is for isotropic consolidation. The starting point for shearing is an equal all-round stress. The starting Mohr circle is just a point on the horizontal axis. But real sedimented soils in nature follow a K0 stress path during deposition and consolidation. The vertical and horizontal stresses are not the same, and the starting point prior to shearing is along the K0 line, not along the horizontal axis. So now the axial compression stress path looks like that, the orange line there, and results in yet a different strength at failure. Another important test is the direct simple shear test. And note that's different than the direct shear test that you might have done in your undergrad soils class. Here the soil is constrained by a series of rings and shears uniformly rather than along a discrete plane through the center of the sample. The vertical and horizontal stresses are originally principal planes. There's no shear stress on them, but when the shear stress is applied to the top and bottom of the sample, the principal stresses change even though those vertical and horizontal stresses stay the same, so the Mohr circle expands. For this sample, the initial stress state after anisotropic consolidation is that dashed circle, and the failure state is the solid circle, and the total stress path is vertical. This figure shows where under an embankment you would see the three key stress paths: triaxial compression under the loaded area, direct simple shear along the base of the potential failure surface, and triaxial extension where the load increment is horizontal. This is a classic plot from Chuck Ladd's 1991 Terzaghi lecture. You've probably seen this before, but maybe didn't know why these strengths are different. But based on the stress paths we looked at, you can see why they're different strengths: triaxial compression, direct simple shear, and triaxial extension. There are two components to the anisotropic strength behavior: the inherent anisotropy due to the mineral grain arrangement, and the shear stress anisotropy due to the initial shear stress in the stress path. To quote from Terzaghi, Peck, and Mesri's text, the undrained strength of a clay or a loose sand is not a constant soil property, and the mobilized undrained shear strength depends on the orientation of the shear plane with respect to the direction of deposition and consolidation, as well as on the mode of undrained shear. In triaxial compression, the shear stresses are increased in the same direction as the already existing geostatic shear stresses. The natural soil structure remains fairly intact until it yields at a small axial strain. In triaxial extension, the shear stresses are increased in the opposite direction to the initial geostatic shear stress. During the test, the shear stresses decrease to zero and then increase in the opposite direction, and considerable disruption of the natural soil structure occurs before the final yield is reached at a relatively large axial strain. The undrained shear strength is the strength that's mobilized under certain stress and shearing conditions. It's valid only for those conditions. So it isn't valid to say the undrained shear strength of the soil is, some constant value. So now we'll review different strengths in drained and undrained shearing. This figure shows four strengths that can be mobilized during drained shearing. The peak strength occurs when a very dense soil is sheared and the soil dilates. As we saw in an earlier slide, The particles have to move over each other and the overall structure expands during shearing. The peak strength may be above the critical state, but with further shearing, the shear stresses will reduce to critical state. The critical state strength is the strength after a relatively large shear strain when there's no longer any volume change with additional shearing and the straining continues indefinitely at the same shear stress. The collapse surface or instability line or undrained yield strength, it goes by a lot of terms, is below the critical state line, and we'll get to more on that on the next slide. One material that doesn't end on the critical state line at extremely large strains is a clay with a residual strength. This is because the material is fundamentally changed along the shear plane by particle reorientation, so that the particles move from a random structure to a face-to-face oriented structure. In this case, the effective stress strength envelope changes with shear strain and can be lower than the critical state line. Depending on the density state of the soil, gradation, mineralogy, stress history of the soil, it may pass through all three of those when it's sheared or go directly to the critical state or residual strength. Now, one caution with limit equilibrium stability analysis is that they don't account for strain incompatibility. Consider if the average shear stress along a potential sliding surface is represented by this purple line here. On average, it's less than the peak strength, so the system might be stable. But if a localized area is overstressed, its strength drops to the critical state or the residual strength, and since it can no longer carry the same load, the stress is transferred to the adjacent soil element, which also becomes overstressed until the whole system failed, even though the average stress was less than the peak strength. The line of peak strengths in undrained shear is called the instability line, and contractive soils will lose strength when they're sheared beyond that. This line is lower than the critical state line, the critical state and instability line. But once the shear stress reaches it, the stress will rapidly drop to the critical state. This plot here shows the same tailings with a variety of stress paths in both undrained and drained shearing and isotropic and anisotropic consolidation. The different test types all end on the critical state line and give the same critical state friction angle. But look at the range in strengths. They're very different. The undrained effective stress path the soil follows to get to the critical state depends very much on if it is contractive or dilative, and that is true of all soils, clays, silts, and sands. Now, if you use the North-Sand constitutive model, you'll be familiar with the critical state stress ratio, M. It's defined in PQ space and is different for triaxial compression and extension due to the effect of the intermediate principal stress. Now, some moderately dense materials exhibit what is called a quasi-steady state undrained strength, where the stress path is initially contractive with positive excess pore pressure before dilating at larger strains. This quasi-steady state strength, that's the ultimate strength there. The quasi-steady state strength is often used for design because there's a view that particle rearrangement at a field scale may inhibit that extra dilation that is seen in laboratory, and hence it might be unsafe to use the strength based on the maximum deviator stress. So as we discussed, real sedimented soils in nature follow a K-naught stress path during deposition and consolidation. The vertical and horizontal stresses are not the same. For a normally consolidated soil, the vertical stress will be greater. Because the in situ stress state won't be on the isotropic line, the in situ stress prior to shearing could be very close to that instability line. And an increment in drained or undrained loading, and particularly a lateral unloading case, or a case with a rising water table where the stress path moves to the left, can trigger instability and an undrained response. We saw that most dramatically and tragically at the Brumadinho tailings dam failure. This figure shows the initial stress close to the instability line. And for the constant shear drain stress path from A to D, it doesn't even mobilize the peak strength before collapse. There will be different degrees of pore pressure generation depending on where the undrained loading starts, whether it's isotropic or an anisotropic stress state. And to get a more accurate representation of the undrained strength under field conditions, the consolidation state should represent the field conditions and follow the same stress path, which means starting from anisotropic or K0 consolidation. So how do we select appropriate strength parameters? So why would we use undrained strengths for analysis when we know that failure of soils is always governed by the effective stresses? Well, if we knew exactly what pore pressures would be generated up to the point of failure, we could use effective stress calculations, but we often don't. And the measured pore water pressures within a slope are in no way indicative of what pore pressures will exist once contractive shearing is initiated. A drained analysis assumes that the effective stress during shear is unchanged from the stress immediately prior to shearing. In undrained shearing, the pore pressures are going to change, will change during shearing far faster than a piezometer can respond, and certainly faster than you could interpret, respond to, and remediate. We talked about estimating the pore pressure changes based on lab tests and Skempton's A and B pore water pressure parameters, but these changes in effective stress are difficult, and I would say practically impossible, to accurately predict at a field scale for the stress paths to failure. And so the undrained parameters incorporate the pore pressures generated to failure. They're built into the strength. Remember, the effective stress friction angle is largely independent of the stress conditions, but the undrained strength is not a material property. It's highly dependent on the stress path. So how to choose your parameters? The key differentiator in choosing undrained or effective stress parameters is not permeability, it's the soil state. Is it contractive or dilative? As Peter Robertson described in the paper I've referenced, where the large strain behavior is contractive, then the undrained strength will be less than the drained strength, and you design based on the undrained strength. Where it's dilative, the undrained strength will be greater than the drained strength, and you should use the drained strength for design because the dilation-induced suction will dissipate with time. And the ICOL Bulletin, International Congress on Large Dams, Bulletin 194, has an excellent description of this, and it notes that drain strengths are unlikely to be relevant at all to a saturated contractive material. So just to drive the point home, here's an example from the text by Duncan and Wright, and you can see that for this test, the shear stress is increased and the drain stress path is vertical, so it's a direct simple shear stress path. The drain strength is 11 kPa, but the undrained strength is less than half that. Again, because of the pore pressure generation during shearing that causes it to hit the effective stress friction envelope at a much lower shear strength. We saw this plot before. The total stress Mohr circle is in red. And because there was positive pore pressure during shearing in this test, the effective stress Mohr circle in green has shifted to the left. The undrained strength is given by the shear stress, where the effective stress Mohr circle reaches the failure envelope. And that's the undrained shear strength there. The undrained strength is related to the initial effective stress prior to shearing there. And for convenience is often reported as an undrained strength ratio, the undrained strength SU divided by the pre-shear vertical effective stress. That results in an undrained strength envelope as shown by that blue line. Now a little bit about lab testing. Common laboratory testing is strain controlled. The computer applies a specified rate of strain to the sample and records the resulting stress on the sample. Although strain control tests are useful to understand the stress strain behavior of the tested soil, they don't strictly represent what occurs in a real world setting where the rate of strain is not controlled. David Carrier in his 1991 paper noted, a tailings dam is more akin to a stress-controlled triaxial test. Once the peak deviator stress is reached, the stress condition assumed in a slope stability analysis, the strain rate to the steady state or residual strength for a cohesionless, undrained, contractive sand can be about 170% per second. Consequently, if an upstream tailings dam is going to fail, it will occur very fast and it will be under undrained conditions. Stress-controlled tests in which shearing occurs under predefined stress levels do not limit the rates at which the sample is strained, and thus better represent field conditions. Stress-controlled triaxial tests on very loose samples of cohesionless soils have shown sudden and dramatic failures even though the drainage valve was left open. In these cases, even though the test was drained, the failure occurred in an undrained manner because the rate of pore water pressure generation within the shear zone far exceeded the rate of pore pressure dissipation. And I'll play a short video from the Fundau forensic investigation to illustrate this. In this test, the video was anisotropically consolidated and then sheared along a constant shear, decreasing mean stress path. There you can see how sudden and dramatic that failure was. So the anisotropic consolidation, and then effectively like a rising water table. So we have the constant shear decreasing mean stress path until it reached the instability line, and then collapse down to its undrained residual strength. So that test was completely drained until it collapsed. Now we'll discuss how not to select strength parameters. There are many examples of design guidance and even some geotechnical engineering texts and case histories that either advocate an incorrect approach to drained versus undrained parameter selection or give unclear guidance that has been misinterpreted. Here's a quote from a popular text on slope stability. For the long-term condition, both the sand embankment and clay foundation would be characterized in terms of effective stress. Pore pressures determined from hydrostatic water levels or steady state seepage analysis would be specified for both materials. And even the USBR design standard states consolidated drained triaxial tests or direct shear tests may be used for free draining foundation and embankment materials. These references don't give a caveat or a qualification about contractive materials, and so some people have interpreted this guidance as being universally applicable. In 2019, David Reed and Andy Fourie gave an excellent two-day workshop on static liquefaction, and in the introduction, they noted the following cases, which all occurred after the Fundau tailings dam failure. When carrying out an investigation of a loose stockpile of sandy material that was experiencing a rise in phreatic level, they expressed a concern at the potential for static liquefaction or undrained shearing. And later, a principal level external reviewer asked them skeptically, isn't that material too permeable to have an undrained strength? When reviewing an upstream raise designed by another consultant, they asked why they weren't considering undrained strengths for the saturated zones. And the response that was given to them was that, well, the rate of rise is low, the coefficient of consolidation is high, so we don't need to worry about undrained strengths. And finally, they were discussing the Fundau failure at a conference, and a professor of geotechnical engineering asked them, wouldn't the sand have been too permeable to fail undrained? So those examples show that there's still a dangerous lack of understanding that exists in our profession, a failure to recognize that sandy materials can fail under undrained conditions, and the trigger mechanism for such behavior can be gradual, drained, and difficult to foresee. And I've seen many examples of this in my own practice, even up to this present time. You know, as I was preparing for this lecture, I was struck by how true this statement from the compendium to the global tailings standard still is. that recent investigations into significant failures of tailings facilities haven't revealed previously unknown failure modes, nor have they required detailed technical research to be undertaken and understand why the failures occurred. Instead, commonly known and well understood mechanisms have been identified as the main physical triggers for failure. So we have the knowledge, as I've shown you, we just have to put it into practice. So is this all really a concern, or is it just theoretical? I already noted the Brumadinho failure, which had a factor of safety using drained parameters of between 1.6 and 2.1. And here's another case history. Andy Furey and David Reed, again from that 2019 liquefaction short course, described the 1907 failure of the Wachusett Dam near Boston. And this is an example, one of many examples of undrained failures of granular materials. Here, the upstream fill was sand and silty sand with some gravel. It was placed loose without much compaction. The permeability was about 10 to the minus 5 meters per second. So that's reasonably permeable. The drain factor of safety was 2.4. The factor of safety using a peak undrained shear strength at the reservoir level was 1.0. And the dam failed suddenly as the reservoir was slowly filling. There was no earthquake and no rapid loading of the slope. The construction was actually finished 3 years prior to the failure. During the reservoir filling process, the loose material was drained, but when static liquefaction initiated, the process following that was undrained. So again, the stress path started with K0 loading as the dam was constructed. As the water table rose, the stress path was constant shear drained. And in that case, the Moore circle doesn't change size, but the pore pressures increase, and hence that Moore circle moves to the left. When the stress path reached the instability line, it collapsed rapidly to the residual undrained strength on that critical state line. And that stress path we've seen has been the cause of multiple failures. So can we monitor for undrained failure and just use the observational method? It's critical to understand what the measured pore pressures are telling you, and even more important, what they aren't telling you. Brown and Jelani wrote in their 2016 paper, the pore pressures that control shear strength are not the ones that exist in situ before failure, but are a sum of in situ pore pressures and excess pore pressures that are generated during the failure or shearing process. And Chuck Ladd in his Terzaghi lecture wrote, a conventional effective stress analysis that uses measured pore pressures gives an instantaneous factor of safety corresponding to the effective stress pore pressure conditions that existed prior to failure. It inherently assumes that a potential failure will occur so slowly that the drain shear strength of the soil will resist failure. The resulting factor of safety is potentially unsafe because it never considers the more critical possibility of an undrained shear failure. At Brumadinho, the piezometers were reading normal water levels immediately prior to the failure. Brown and Jelani in their excellent paper called Common Errors in the Slope Stability Analysis of Tailings Dams described the need to distinguish between 3 types of pore pressures when doing a stability analysis. There's in situ pore pressures, which are the pressures that are present below the water table before the initiation of failure. They can be measured by field tests or by piezometers, or they can be estimated by a seepage analysis. Then there's loading-induced excess pore pressures, which are induced due to rapid loading of saturated materials. With time, these excess pore pressures are expected to gradually dissipate, and they can also be measured in the field with piezometers. Finally, there's shear-induced excess pore pressures, and these are pore pressures that are generated over and above the in-situ and loading pressures during shearing of contractive materials. These pressures cannot practically be measured in the field. However, they can be measured in the laboratory with an undrained shear test. Simulation of these shear-induced pore pressures using constitutive soil models is possible, but requires extensive calibrations to lab tests, which can make the whole process very complex and difficult. To overcome this, the standard practice is to adopt the undrained strength approach, which inherently accounts for the shear-induced pore pressures in a practical way. So we'll give the last words on this topic to Chuck Ladd and David Carrier. Although piezometer data are essential for undrained strength analysis and to evaluate field consolidation behavior, they seldom provide a direct warning of foundation instability, since dramatic pore pressure increases occur, if at all, just prior to or during actual failures. And David Carrier's 1991 paper, Stability of Tailings Dams, has a section titled An Example of How Not to Do a Static Stability Analysis Based on Drain Strength Parameters. He describes a dam that failed just after the designer had calculated that it had a drain factor of safety of 1.7 and concluded that in general, geotechnical engineers should do both effective stress analysis and an undrained strength analysis. Whichever yields the lower factor of safety controls the design of the embankment. So, conclusions. Loose or normally to lightly over-consolidated soils can fail in undrained shear, regardless of permeability. The undrained strength is a means of representing the soil strength that includes the shear-induced pore water pressures. Drained or undrained strength should be selected based on whether the soil is contractive or dilative, not based on its permeability. For contractive soils, the drain strength is higher, it's often much higher, than the undrained strength, so the undrained strength governs. For dilative soils, the undrained strength is higher than the drain strength, but the negative pore water pressures are going to dissipate over time and reverting to the drain strength. When using undrained strengths for analysis, these need to be determined for the correct mode of shear, as the undrained strength can vary greatly depending on the stress path. So this is by no means a comprehensive look at basic soil models, but hopefully it's enough background to give you a foundation to learn further and to understand what you're reading in more advanced texts and papers. Learning in geotechnical engineering is truly a lifelong process. So here are the references that I've used. And again, I haven't told you anything that's new. I've simply collected the concepts from texts and key papers. I've highlighted two that I think should be absolutely essential reading. ICOL Bulletin 194 and Chuck Ladd's 1991 Terzaghi lecture. That's a starting point, and there's a lot more reading to do beyond that. And thanks. I think we have a few minutes for some questions or for some insights that others have based on their experience.
Okay. Thank you very much, Professor Scott. So there's any question here in the room? For the people that is online, you can please raise your hand, and yeah, I will give you the mic, but please raise your hand before so we can make it this in an organized fashion. Any question here?
Looking at one from the meeting chat here. So the question is, what process do you follow to select the vertical effective stress when using an undrained strength ratio? Do you account for any consolidation when planning multiple raises or the potential for shear-induced consolidation? So yes, when you're constructing slowly, you would account for consolidation that's occurred prior to the next load increment. And so, you know, the system needs to be stable prior to each load increment being applied. So if you've raised it, let's just say you've raised a dam up halfway and you're going to wait for some consolidation to occur before raising the next stage of the dam. Let's just say simply we're only raising the dam in 2 stages. So as long as those pore pressures have dissipated, it's kind of like, if I go back a few slides here to 3 different types of pore pressures, it's sort of like we're talking about item 2 here, load-induced pore water pressures. Once those load-induced excess pore water pressures have dissipated, then you can account for that, that new effective stress in your undrained strength ratio. And that would be the starting point. That would be how you would calculate the undrained strength prior at the time of the next load being applied.
Okay, we have another question. This is, when referring to lightly consolidated soil, what OCR ranges will reflect that?
Yeah, I think you know, typically when you look at the sort of spacing ratio between the critical state line and the normal compression line, that spacing ratio is usually about 3 to 4. It might vary a little bit for different soils, but usually an OCR of less than 3 or 4 would be considered lightly over consolidated. If it's more than 3 or 4, it would be heavily over consolidated. So that's a very rough guide to what would tell you if you're expecting a dilative or contractive behavior.
Okay. So if there is no more questions, so we can conclude today's presentation. Thank you everyone for being here. Thank you, Scott, for the great presentation. Yeah, see you next week, everyone.
Hey, thank you.